Hello everyone, I'm J Wildberger. Today we're going to be looking at tips and tricks for computing cyclotomic polynumbers. So these are these important polynomials or polynumbers that are connected with algebraic number theory, with Galois theory, and just generally with just interesting factorization of expressions like 1 minus alpha to the n. Okay, so the key fact about these things is that there are irreducible polynumbers phi sub n, one for every natural number, 1, 2, 3, and so on. These are polynumbers with integer coefficients, and they satisfy that 1 minus alpha to the n, that expression as a polynomial or polynumber, is a product over all divisors d of n of phi sub d. So these things give us the factorizations of these important polynomials or polynumbers. Now, from my point of view, this is not entirely set up correctly, as I've mentioned to you in our last video. There's issues, foundational issues with the setting up, the proving of the irreducibility especially. Okay, so I think there's some opportunity here for people to look at this again with fresh eyes, so maybe you can become famous and really put this all on a solid foundation without any infinite waffling, okay? Strictly, purely algebraically, finite operations, arithmetic, everything is on the page. That's what's required. Okay, but nevertheless, we can compute these things because we can just factor these kinds of things. And here are the first few small cyclotomic polynumbers up to phi sub 9, which is 1 plus alpha cubed plus alpha to the 6. Okay, today what we want to do is we want to establish some facts that allow us to, anticipate what these things are going to be looking like, what various relations there are between different cyclotomic polynumbers, and ultimately, how do we actually, come up with some values for larger values of n. Okay, so here are some additional interesting and important facts about cyclotomic polynumbers, which we can establish at least empirically. We can observe that these things are true for the range of values that we're looking at, and we can aspire to understanding why they are true. But that, of course, that requires a sort of a prior theory of what these things are in the first place. So it's premature at this stage to really inquire deeply as to how we should prove all of these things. But I think there's a lot to be done here, a lot of things to think about if you're an amateur or an undergraduate mathematician. How do you establish some of these facts? So first of all, the degree of these polynumbers. The degree of phi sub n is actually phi of n, okay, where this little phi of n is Euler's totient function. It counts the number of natural numbers which are less than or equal to n, and which are relatively prime to n. So for example, phi of 30 is 8 because the natural numbers which are less than or equal to 30 and relatively prime to it are, well, there's the number in this set. The set 1, 7, 11, 13, 17, 19, 23, 29. These are the numbers less than or equal to 30, which are relatively prime to it. And there's 8 of those, so that's what phi of 30 is. That's telling us that the cyclotomic polynumber phi sub 30 is going to be of degree 8. Okay, and there it is right there, actually. Okay. 1 plus alpha minus alpha cubed minus alpha to the 4th minus alpha to the 5th plus alpha to the 7 plus alpha to the 8. It is of degree 8. The second fact, which we've already talked quite a lot about, is that if p is a prime, then phi sub p is simply the sum of all the powers of alpha from alpha to the 0 up to alpha to the p minus 1. Now, third fact. If p is a prime and we're interested in phi of a power of a prime, p to the k, phi sub p to the k, that's equal to phi sub p, which looks like this, evaluated at alpha to the p to the k minus 1. So for example, let's say we're interested in phi sub 9. Well, 9 is equal to 3 squared. 3 is a prime. So this rule is telling us that we should take phi sub 3 and evaluate it to not alpha to the 3 squared, but alpha to the 3 to the 1, namely alpha cubed. So we take phi sub 3, which is 1 plus alpha squared, and we substitute alpha cubed in for alpha, and we get 1 plus alpha cubed plus alpha to the 6. So these two formulas very clearly lay out what the cyclotomic polynumbers are, where the number in question is a prime or a power of a prime. So for example, suppose we want to factor 1 minus alpha to the 81. Now 81 is a power of 3. It's 3 to the 4th. And the divisors of 81 are just all the other powers of 3 which are less than or equal to 4. So this thing should factor into the cyclotomic polynumber phi sub 1 times phi sub 3 times phi sub 9 times phi sub 27 times phi sub 81. And these factors illustrate the previous theorem. So we already talked about phi sub 9. Phi sub 27 is equal to 3 cubed. So you have to evaluate this. What you take is you take the phi sub 3 and you replace the alphas with alpha to the 3 to the 2. In other words, alpha to the 9. Okay, so you replace that alpha with alpha to the 9, that alpha with alpha to the 9, and that's what you get there. And then phi sub 81 is the same kind of thing where you replace alpha now with alpha to the 27. In a similar direction, 1 minus alpha to the 64, now we're talking about a power of 2. And so there's factors, 1 for each of the powers of 2 less than or equal to 64. And we've seen some of them already. There's phi sub 2, phi sub 4, phi sub 8, phi sub 16, phi sub 32, phi sub 64. And it's the same pattern. Basically, we're just plugging in to phi sub 2 the appropriate power of alpha to the power of 2. Okay, now we come to a really important rule, perhaps the most important rule, which tells us how to get phi of a value like this, where you have a prime, p, and another factor, m, which is relatively prime to p. Okay? So p is a prime, and we're assuming that p and m are relatively prime. They have no common factors. Then phi sub p times m times phi sub m is equal to phi sub m of alpha to the p. So assuming we know what phi sub m is, we know this factor and this factor, we can then calculate phi sub p times m. So for example, suppose that p is 5 and m is 12. Maybe we're interested in calculating phi sub 60. The rule says phi sub 60 times phi sub 12 should be equal to phi sub 12 evaluated at alpha to the 5. 5 is the prime. Okay, what is phi sub 12? Here it is here. It's 1 minus alpha squared plus alpha to the 4th. So if we solve for phi sub 60, we see that it's phi sub 12 to the alpha to the 5th. So we have to replace alpha with alpha to the 5th. So we get 1 minus alpha to the 10 plus alpha to the 20 in the numerator. And in the denominator, just phi sub 12. So we can evaluate this by doing a division. We can divide one polynumber by another polynumber, and that's a very nice computation that we can actually do by hand. And in this case, the answer is this thing here, 1 plus alpha squared minus alpha to the 6 minus alpha to the 8 minus alpha to the 10 plus alpha to the 14 plus alpha to the 16. So that's phi sub 60. Another interesting special case is when p, the prime, is actually just 2, and then the m is just an odd number so that they're relatively prime. In that case, the formula is phi sub 2m times phi sub m equals phi sub m evaluated at alpha squared, which we can rewrite if we like as phi sub 2m is the quotient phi sub m of alpha squared over phi sub m. So for example, if say we're interested in phi sub 14, 14 is 2 times 7. So we're going to get phi sub 7 of alpha squared over phi sub 7. Well, phi of 7, that's the one that we know because 7 is a prime. So we're getting all the powers of alpha. In the denominator here, for example, 1 plus alpha all the way up to alpha to the 6. And then in the numerator, the same kind of thing, but alpha replaced with alpha squared. So 1 plus alpha squared plus alpha to the 4th all the way up to alpha to the 12th. So we have to divide this thing by this thing. Now it's not obvious that, that this quotient actually is a well-defined polynumber. Typically you divide one polynumber by another, you expect to get a remainder. Okay? So it's pleasant that, that there is a division that's possible here. And the result of that division, which you can obtain by doing it longhand, is 1 minus alpha plus alpha squared minus alpha cubed plus alpha to the 4th minus alpha to the 5th plus alpha to the 6th. And that has a particularly sort of attractive form, and we'll see some reason for that a little bit later. Here is the other really important rule that sort of complements the one that I've just shown you. It's the case when you have p a prime and p divides m. So m now is not relatively prime, but p actually divides m. Then it still relates phi sub pm to phi sub m, but the relation's a little bit simpler. So now phi sub p times m equals phi sub m of alpha to the p. So for example, phi sub 75, 75 is 15 times 5. So in this case, the prime p is 5, and the m is 15, and 5 does actually divide 15. Okay, so then the rule is that phi sub 75 is phi sub 15 evaluated at alpha to the 5. Now phi sub 15 was that interesting thing that we'd already seen before, and we just take that thing and replace alphas with alpha to the 5. So we get 1 minus alpha to the 5 plus alpha to the 15 minus alpha to the 20 plus alpha to the 25 minus alpha to the 35 plus alpha to the 40. So in principle, these last two allow you to kind of bootstrap yourself up. If you have a number n, which is a product of primes, then you could at least, if you wanted to sort of work your way up using these two relations, calculating them step by step. Okay, and our final little rule, which we've seen in a special case, is that if m is an odd number bigger than 1, then phi sub 2m is phi sub m to the minus alpha. So you just take phi sub m and you put minus signs in front of all the terms with an odd exponent. So we saw that in the case of phi sub 14. Okay, so those are some nice tools that allow us to sort of build up cyclotomic polynumbers from smaller ones, involving the prime decomposition of the natural number n that we're starting with. I want to illustrate some of these things now with a specific example. I want to calculate phi sub 1001. Or at least show you what it looks like. I'm not actually going to do the calculation, but I'll show you the result of the calculation. So I think it's interesting to make some contact with some larger values so we can appreciate both the complexity and the beauty somehow of these objects. So first of all, 1001 is quite a nice number because it's the product of 3 primes, 7 times 11 times 13. 3 consecutive primes, actually. Okay, so this number, its divisors, are just going to be consisting of products of subsets of these 3 primes. So aside from the primes 7, 11, and 13 themselves, and we know what their cyclotomic polynumbers look like, we also have the factors 7 times 11, 7 times 13, and 11 times 13. And so it's reasonable to calculate those first. So let's look at phi sub 77. Well, if we think of that as 11, times 7, and maybe we think of the 7 as being the prime, so it's 7 times 11, then the formula would be that it's phi sub 11 of alpha to the 7 over phi sub 11. On the other hand, if we sort of interchange the roles and think of it as 11 times 7, 11 is now the prime, then it's phi sub 7 evaluated at alpha to the 11 divided by phi sub 7. And in either of these cases, this is in some sense straightforward to do because we know what, say, phi sub 7 is. It's 1 plus alpha all the way up to alpha to the 6. So we have to substitute alpha, replace with alpha to the 11. Okay? And then we just have to divide it longhand if we don't have a computer, but we can do that, by phi sub 7. And then you're going to get some nice polynumber. There will be no remainder, which is what we're sort of being told here. And the result of that is actually this thing here. Okay, this is phi sub 77. And let's just go through it, okay? It's interesting. 1 minus alpha plus alpha to the 7 minus alpha to the 8 plus alpha to the 11 minus alpha to the 12 plus alpha to the 14 minus alpha to the 15 plus alpha to the 18 minus alpha to the 19 plus alpha to the 21 minus alpha to the 23 plus alpha to the 25 minus alpha to the 26 plus alpha to the 28 minus alpha to the 30 plus alpha to the 32 minus alpha to the 34 plus alpha to the 35 minus alpha to the 37 plus alpha to the 39 minus alpha to the 41 plus alpha to the 42 minus alpha to the 45 plus alpha to the 46 minus alpha to the 48 plus alpha to the 49 minus alpha to the 52 plus alpha to the 53 minus alpha to the 59 plus alpha to the 60. Okay, that's quite cool. We immediately observe that although the exponents are not entirely predictable, the coefficients are. The coefficients are just alternating, plus, minus, all the way through. And the other thing that we observe, if we look at it for a second, maybe a few minutes, is that there's a kind of a palindromic aspect to this. And the whole thing, if we wrote it out, is symmetrical around this sort of midpoint. Okay? The thing has degree 60, because phi of 77, the way you calculate a totient of this is the number of numbers less than p, if p is a prime, which are relatively prime, is p minus 1. Okay? So phi of 7 is 6, and phi of 11 is 10. And this totient function is multiplicative if the things are relatively prime. So a phi of 77 is 6 times 10, which is 60. So we do expect this thing to be of degree 60. And 30 is sort of the halfway point. And the thing is symmetrical around that. So in other words, like if we say at 30, if we go up, the next one is up 2. Okay? But the previous one was down 2. The next one's up 2. That one was down 2. Then you go up 1, down 1, up 2, down 2, etc. Okay? So there's a symmetry. So knowing that, if you just knew this thing up to the halfway point, you could then just use the symmetry to deduce what the other one, or the other half, was going to be. Raises the questions like, why is that happening? Why are these coefficients alternating in sign, and why is there a palindromic aspect? That's a great thing to think about if you're a sort of an amateur mathematician. Okay, on this rather intimidating slide, I'm showing you also phi sub 91. 91 is 7 times 13, so that's another factor of 1001. And I'm also showing you phi of 143, which is 11 times 13, which is the other factor. Okay, and the same things that we've observed are happening here. There's an alternating aspect of the signs. There is a symmetry about this sort of middle term, so it is palindromic. And the same thing with this larger one, still alternating. But if you actually look at the exponents and try to figure out, which ones are appearing and which ones aren't, that is not at all so obvious. Okay, that's not at all so obvious. And if you can give me a little rule that explains what's happening here, I would be very interested. Okay, Same thing for this one. How do you tell whether, 55 is on here or not? Why is 55 here and 54 not? So what's the reason? That's, to me, seemingly quite a subtle issue. Great, so now we're ready to tackle phi sub 1001. So I remind you that that really comes about by trying to factor the expression 1 minus alpha to the 1001. And we know that that's going to factor, at least if we, have learned about cyclotomic polynumbers, it factors as a product of the cyclotomic polynumbers, 1 for every divisor of 1001. And the divisors are 1, and then the 3 primes, 7, 11, and 13, and then these 3 pairs of primes that we've just looked at, 77, 91, and 143. And then there's the one more, the extra factor, which is the cyclotomic polynumber, phi sub 1001. So, in principle, having all of these here, okay, you could take this thing here and divide by this thing here, okay? And that's one way of getting phi sub 1001. You could do that by hand. It would take you, better part of a day probably, but you could probably do that. However, with computers, you can exploit the fact that computers are really good at factoring polynomials. This is one of the great developments of sort of modern computer algebra systems. They have really great polynomial manipulation routines. They can deal with really big polynomials, and even things like this, they can factor this thing. My computer will factor this thing in less than a second. So it will spit out this factorization very quickly, and then it's just a question of identifying which one is going to be phi sub 1001, and it's the biggest one. Okay, but that's exploiting the fact that your computer can do this. If you don't have a computer to help you, well, then you have to use these tricks that I've been showing you, okay? But even with the computer, you still have to identify which of the factors is the one that you're interested in. Okay, and here, drum roll, is phi sub 1001. So it took me a while to write this down, so I hope I haven't made too many mistakes. I hope I haven't made any mistakes, but I hope. But anyway, let's have a look at it. One thing that we observe is that the nice kind of patterns that we saw with these three things is no longer happening. Okay, this is no longer alternating plus minus ones. There's pluses, like here, there's a string of pluses up to alpha to the 6, and then there's minus alpha to the 11, minus alpha to the 12, and then suddenly minus 2 alpha to the 13. Whoa, okay? It's not just plus or minus 1. There's a 2 that's appearing here. Now, in the early days, people thought that perhaps all the cyclotomic polynumbers had just coefficients of plus and minus 1. The first place where you see that that's not the case is when you take the product of the 3 simplest or smallest primes, 3, 5, and 7. That's 105. Okay, so phi sub 105 is actually the first cyclotomic polynumber whose coefficients are not all 1 and minus 1. There's a 2 there. Okay, and here there's also some 2s, but there's not a lot of them, but I have underlined them in red just to point them out. Okay, so the pattern continues. There's minus 2 alpha to the 13. There's a whole bunch of 2s here. There's actually that one there, and then alpha 14, alpha 15, alpha 16, alpha 17. And then minus alpha 18, minus alpha 19, plus alpha to the 24. There's a whole string of pluses all the way up to alpha to the 30. So I'm using 3 dots. Okay, that means that you have to go alpha to the 24, alpha to 25, 26, 27, 28, 29, up to 30. Okay, and then here there's another little string and so on. And then it keeps on going. And if you're just reading this, it's really hard to predict what's going to happen at any given point. It's really tricky. I don't know how to do that. I think it'd be really interesting to be able to do that, but I have no idea if that's possible, that's feasible. Anyway, so I've listed them down to, there's a string here, 59, 260, 261, and it then continues. Okay, so we're just pausing here after alpha to the 261. Okay, and then it continues. So there's then 263 up to 265, pluses and minuses. There's a few more 2's that appear. And here we arrive at the central spot. Okay, it's palindromic, centered at this. This is alpha to the 360. Okay, and then it carries on, and there's some more minus 2's and strings of plus and minus 1's, and it's all a little bit unpredictable. Except that at this stage here, if you know it up to here, then in fact you can reproduce the next because it's all palindromic, centered around here. Now we get up to alpha to the 500, so it carries on. Okay, so then after that we get alpha to the 508, and then it carries on, a few more 2's, string of 2's there, and finally alpha to the 714 up to alpha to the 720, and that's where it finishes. It's of degree 720 because that's 6 times 10 times 12. So that's it. We've had a good look at a bigger cyclotomic polynumber. And I hope it's fascinated you a little bit and raised some really nice questions for amateur mathematicians, or maybe actually even regular mathematicians, to think a little bit more deeply about. The actual nature of the coefficients and the exponents that appear in something like this is very interesting. Can we say anything about which powers occur and which don't in a given cyclotomic polynumber? That's a kind of interesting challenge. So in our next video, we want to go back to the cyclotomic field story, and I want to explain to you how we can construct these things without any cheating. Hope you'll join me for that. I'm J Wildberger. Thanks for listening.